With this, we actually get to the last talk of the workshop, which brings us back to the localization challenges that were part of this workshop. And we are going to have the second place entry on the autonomous vehicle challenge, which will be presented by Martin Humenberger. Martin?
Yes. Can I share my screen already?
Please.
Perfect. Which one is it? This. Here we go. All good? Okay, I hope you can see my screen now and hear me. So hello everybody, my name is Martin Humenberger and I'm very happy to present some of our work on visual localization today. In detail, I will talk about late fusion of global image descriptors, as well as our new data format and toolbox named Kapture. This is joint work with Yohann Cabon and Gabriela Csurka, as well as other colleagues from the lab from Naval Labs Europe. So my presentation consists of two parts. I will first give a brief introduction of our method. In detail, I will present our idea of late fusion of multiple types of global image features. Then I will present the results we have achieved with this. Then in the second part, I will introduce Kapture, and I will give you a demo of how it can be used to actually reproduce some of our results. So following the traditional pipeline, our method consists of two parts. The mapping part computes a 3D representation of the environment. The localization part computes the precise position of the camera in this map. And we use our work R2D2 for local feature extraction. And we use image retrieval to find image pairs to match. We do that for both mapping as well as localization. And for the structure for motion parts in the pipeline, we use CallMap. For image retrieval, we investigated various global feature types. In particular, we ran experiments with NetFlat, DenseFlat, NetFlat, our own work, APGEM, and very recent work, DELG. Our experiment on a selection of challenging datasets showed that none of them is a clear winner, as you can see here in this plot. The reason for this might be the descriptor design itself or the training data used. Actually, to answer this question, more research would be necessary. However, instead of retraining the descriptors, we wanted to see how far we can get by using a combination of them. Essentially, we would like to find a fusion strategy which outperforms each individual descriptor, ideally on all of these datasets. To get started, we used our early work on late fusion. Late fusion means that we first compute the similarities for each descriptor individually and then apply a fusion operator. We considered multiple operators round robin, which selects top ranked images from a different descriptor from the different descriptor types in a circular order, min and max, which combines the lowest and the highest similarities, mean and power, as well as generalized harmonic mean, where both tend to be more robust against outliers than arithmetic or geometric mean. Our experiments showed that generalized harmonic mean as well as mean and power perform very well. As you can see, they produce higher accuracies than all individual descriptors across the data sets we used. It's the red bar here. So applying our late fusion strategy to the challenge datasets results in the following ranking on the main benchmark tables. We ranked first on Aachen 1.1 and Robotcar version 2. We ranked second on Silda. We ranked third on extended CMU and 14th on InLog. This actually confirms what Thorsten said about InLog. It is indeed a very interesting dataset. Now let's move to the second part of my presentation. So during our work on visual localization, we very often face the challenge that many datasets are provided in different formats and sometimes not, and are because of this sometimes not easy to use. This does not only mean that data importers and exporters might need to be adapted, it almost always means that coordinate systems or camera parameters need to be transformed as well. To facilitate all this, we created Kapture, and we hope it will boost research and development activities in the field. But what is Kapture? So first of all, it is an open source data format and toolbox for visual localization and structure for motion. it can be used to store sensor as well as reconstruction data, such as local or global features and matches. And because of that, it can easily be used to implement various processing pipelines. And finally, and very important, downloader provides upload data sets in ready-to-use Kapture format, like all the data sets we used for this challenge. Kapture comes with a set of examples that show how it can be used. And I would like to show you reproduce some of our results. In the interest of time, I will skip some of the videos, some of the steps, but all the steps are documented on. Note that in this demo, I show how the provided tools can be used. However, Kapture can easily be used as a library in your own Python code as well. So let's start. We will first install Kapture, then we will download the Aachen Day-Night dataset, the image retrieval. We will do local feature matching using these retrieved pairs. We will use call-map for mapping, and we will use call-map for localization. And finally, we will evaluate the results on visuallocalization.net. And everything will be done from scratch. So let's start with installing Kapture. This is quite easy. You type pip install Kapture to install all the tools. And then you can clone the repository from GitHub, which gives you the source code if you want. And it also gives you some examples. And we will use our first command, Kapture print, to open one of these samples, and then you see what is inside. It consists of a couple of 3D points, trajectories, sensors, cameras. This is really just a small example. Then we will download the Aachen Day-Night dataset. For this, we will use our built-in downloader. It has a couple of commands. First, we update the available datasets. Then we use the list command to print them, to show them. We see we have Aachen Day-Night, we have extended CMU, we have robot car, we have Silda, we have Inlock. And as you can see from the download links, the location of the dataset does not change, neither does the README or the license or the references, of course. And then we use the install command to download all available Aachen captures, which consists of the mapping and the query data. Then we will extract the global features. For this, we will first clone the, we will install the dependencies for APGem. Then we will clone the source code repository of APGem. Then we'll download the pre-trained model. And then we use a command called extract capture provided in the APGem repository, which takes a capture as input and computes the global features for all images. Next, we will extract local features. We use for this R2D2. Again, we start easy with git clone the R2D2 repository. As you will see, it already comes with pre-trained models. And then we again use a script called extract capture, which is part of the R2D2 repository, which takes a capture as input and computes the local features for each image. Note that for the last two steps, we actually merged all the mapping and the query images into one capture for easier processing. So next step will be get image pairs with image retrieval. For this, we use a script called Kapture compute image pairs, which will launch first using only the mapping data to generate the mapping pairs. Then we'll launch the same script using the mapping data and the query images to get the query pairs. Next step will be the local feature matching. For this, we use Kapture compute matches, and we'll do that for the mapping pairs and for the query pairs. Then we use all this data to compute the 3D reconstruction using call-map, again with script. And then we have another script for localizing our query images in this 3D reconstruction, again with call-map. And then finally, we can evaluate these results on the website. For this, we first need to convert from Kapture format into the website format. Obviously, there's another script for that. And as you can see here in the text file, this looks as you might expect. And then you can go to the visual localization website. You can upload your file, and after some processing, you will see in the benchmark table, if you go in our case to Aachen version 1.1, here we using the data computed demo, we are ranked third. So of course, we're happy about any types of external contribution. For example, you could provide your own data sets in Kapture format so that they can be made available in the downloader. Similar to what we did for R2D2 and APGEM, you could provide scripts for data processing using Kapture. You could integrate Kapture support in your own pipeline. This will enable the easy use of many different data sets with your pipeline. For example, I'm already discussing with about the integration of Kapture to HLog with Paul Edouard. And of course, we can provide any help you might need for all these tasks. And we are happy about any kind of feedback and suggestions for improvement. So to conclude, in the first part, I presented how late fusion can improve image retrieval-based visual localization. In the second part, I introduced Kapture, a versatile data format and toolbox to facilitate future research and processing in visual localization and structural motion. And let me give a big thanks to the organizer of this workshop. Let me finish by pointing you to some useful links and references. So thanks a lot for your attention. And if there is still some interest and energy for any questions or discussions, please do not hesitate.
Thank you very much, Martin. Are there any questions from the audience? If yes, please use the Q&A button. And yeah, thank you very much for the effort of building Kapture. I mean, this looks like an amazing tool that will be very useful for the community. So how hard is it actually to add additional data sets? Is that something that you do centrally, or is it easy for the community to essentially add support for new data sets there?
Yeah, that's a very interesting question. And we have in the repository, we actually also provide the code and tutorials of how we converted all already available data sets into Kapture. It's basically, you need to understand the data set, of course. You need to understand how the camera coordinate systems work and things like this, which you need to do anyway. And then it's essentially you running some Python scripts to convert one text file into the other, basically. Because Kapture is, I mean, it depends what you would like to save or what you would like to provide. For example, if it's just like the images and the poses, this is a text-based format, so this is quite easy to do. But what we would like to do in the future is actually also providing in the downloader already extracted data. For example, extracted R2D2 features or extracted SIFT features or dense flat, so that it's not everybody needs to re-extract everything, and that you can test and evaluate these features more easier. But long story short, if you have a data set and you would like to make it available in the downloader, which is very convenient, then you can just check out our examples or really just ask us and we will help immediately doing that.
Great. But would it also, you had this Kapture list, print list of data sets example, would it automatically, is there a way to automatically list it there, or is there some sort of review process going on?
So this is, I mean, we need to make sure that, so we need to manually add them so far. This is like really the first version of this. And there is a review process going on by ourselves. So we check that the licenses are all correct, that the README and the references are preserved, and that nobody gets in trouble doing this. Okay, yeah, that makes sense.
Are there any questions from the audience or from the other panelists? Please feel free to ask. Will Kapture also contain, so will you make available the setup that you used for this, your entry in the challenges? Is that already in there? Will that be available later?
It's not in there yet. So this is something which is which has been discussed at this workshop earlier. So we are Currently, all the open source part it contains mainly the data format itself plus some tools using it. Of course, we use it as pipeline as well, right? So we achieve very good state-of-the-art results with this, and parts of it, as I showed today, is already open source. Not all of it, and especially this fusion part it's not. It obviously works, but it needs more investigation and a little bit more in detail development. And we would like to make as much as possible open source, but there are currently no concrete. I cannot tell when this will be done.
Okay, thanks. There's one question regarding Kapture and robot car. Mm-hmm. Does Kapture utilize the fact that the dataset was captured by a rig with multiple cameras with known transformation matrices?
So we do that. It's currently not part of the open source release, but that's exactly what I meant earlier. So we implement our pipeline fully on Kapture, and in our implementation we use the rig configurations. And actually we already, I mean, again, we have a script which is actually doing that, which takes a capture. You have to know that this data format internally supports rig configurations. So then it totally makes sense to have a script which can compute the localization leveraging this rig configuration. So this is what we have done, but it's also not yet open source. But we use open source tools. So actually what we did is write some wrapper around this, and as soon as this is cleaned up and made a little bit nicer, we can for sure release it.
Yeah. Thanks. There's another question. Is there a way to add cameras, lidars on RGBD devices?
Very good question. So currently we actually indirectly support this. So we have LiDAR data and we have RGBD data, and something in between, or I mean, some other point clouds. For example, the in-log data set, as you all know, consists of images and 3D data, and this can also be read with Kapture. It's currently not perfectly documented, but if you download the in-log data set, then there is a README which shows you how to open any kinds of 3D data associated with the images or the timestamps in your data set. Mm. So there is a way of doing it, and we used it for LiDAR scans and the in-log data set.
Great, thanks. There don't seem to be any more questions from the audience. So thank you again, Martin, for the great talk.
Thank you.